will be as soon as I go back here. Now it will join. There you go.
Yes, it's switching. Okay. And I see here what's showing there. Okay. Because I can see this.
Yes. You can do plugging. It's okay to use head microphone.
Ah, I have now two things. That's of course.
You're confused.
I'll get started then. This one seems to work.
Things are getting more complicated because my left hand is not very good.
Okay, we can try the other one.
No, I mean using two things. I could press it. Or I could. No, that's okay. I'll get. It's okay. I'll get used to this. That's okay. Because this thing will just slip away.
If you need to move slides, you can just tell me and I can also speak for you.
No, it's okay. I think I'll get a hang on.
So are you all set?
I'm fine. Okay, so you should clap or something. Clap.
All right, welcome back, everyone. Hopefully everyone had a nice lunch. We are pleased today, this afternoon, to have Dmitry Kozlov with us, who will speak to us on simplicial models in distributed computing.
Okay, so thank you. Let's see. So this is optimal distance problem. So first, thank Pavel and other organizers for inviting me to this beautiful place and this beautiful new hall. So I'll speak about simplicial models in distributed computing. And what I planned was I will do three parts. In the first part, I will talk a little bit about what distributed computing is, because I think that's quite helpful. This part will not contain any topology or simplicial complexes. In the second part, I will bring them together and show how simplicial models appear in distributed computing. And in the last part, I wanted to talk about specific question in distributed computing, where on one hand, the topological simplicial models have been helpful in understanding certain questions about complexity. And on the other hand, at the same time, in the opposite direction, they led to interesting questions and still open interesting questions about certain simplicial complexes, certain triangulations of simplices, and labelings on these triangulations. So in the end, we have a framework with open questions where distributed computing is not mentioned anymore, but you have questions which need to be answered. So before I start with all this, I just wanted to start very quickly about how what we're thinking about when we talk about combinatorial algebraic topology. So this conference is in applied topology, and so in combinatorial topology, we were was also an area which was rather developed already before applied topology came to its current prominence. And in this area, you study combinatorial cell complexes. I explicitly say cell complexes, not necessarily just simplicial complexes. And you also study them by combinatorial means. So it's kind of developed in a certain sense on the crossroads between algebraic topology and combinatorics, where we can specify a little bit what we mean. This is all a little bit historical perspective, but still what we mean by combinatorial cell complexes. So when you try to make cell complexes, so cell complexes, we just think about something built out of cells, so W complexes. And the first thing you can try to do is to make them combinatorial locally, which is something standard done in algebraic topology, where you want to replace simply continuous maps, which you glue with by some combinatorial descriptions. So typically it could be simplicial complex, or it could be cubical complex, or it could be a complex where instead of simplices or cubes, you have direct products of simplices as building cells and combinatorial rules of how to put them together. That's something which is locally combinatorial. But in this area, more important is that they're also globally combinatorial, which means that not only you have simple gluing rules, but also you have an enumeration and indexing of all of the cells which you have in your complex. And you have some sort of combinatorial description of what they are. Moreover, the way these cells are put together is also described as a combinatorial rule. So as an example, we could have, for example, let's say we have a graph and we have all graph colorings. Let's say we fix a certain number of colors which we want to use, which is large enough, so they actually exist. And we could have all graph colorings as vertices. And then we could have higher dimensional cells glued in according to how these colorings interact with each other. So we could start by gluing in an edge between two graph colorings as they differ in one vertex, and continue with gluing in higher dimensional cells, which will be direct products of simplices to reflect some sort of commuting relation between this graph colorings. That would be a typical example of a combinatorial cell complex, which have been used, for example, in studying graph colorings in combinatorics. What I will talk about today will be combinatorial complexes where you have a similar combinatorial description, but which comes from computational models in distributed computing, where in this case, you will have a certain computational model which will be several processes, and the vertices will be the views of the various processes on the computation as it unfolds, and the cells will be various executions. In the distributed computing, there will be not one path of execution, but there will be several possible execution of the protocols depending on what happens, because there is uncertainty in the model. Anyhow, but this is like a general view on just what we want to achieve. We want to have some sort of combinatorial simplicial, in this case it will be simplicial, combinatorial simplicial model, which we can hopefully have purely mathematical questions which need to be answered, but which comes from the field of distributed computing. So yeah, so this is just a slide with a reference to this combinatorial direct topology. As you see, it's from 2008, so that's a long time ago. So today I want to go to distributed computing, and this is an area which is, well, I'll talk about theoretical distributed computing. So theoretical distributed computing is an area within the theoretical computer science, just like complexity theory, other things. And so it grew in the 60s and the 70s from the fact that one wanted to understand theoretical aspects of computing in networks. Originally, also in the chip design, because one wanted to know what kind of operation you could implement on hardware level in the chips to be able to compute certain things quickly and so on. So there's various models, and I'll just go through this so that so certainly there are thick books written about this, so I'm not going to go through this in detail, but I hope to give you an impression of what I'm talking about here is application, and then hopefully be able to connect it to simplicial models. Yes. Okay. Byzantine failure. Well, I wanted to go through the list, but Byzantine failure is when you're communicating with the processor and he delivers information which might be faulty. Right. So that would be typical. For example, if you open a newspaper, most of what you read would be an example of Byzantine failure. So this is corrupted information, right? So the setting is like this. So you have n processes which want to perform a certain task. And one thing which took me a while to understand in all of this, because I was coming from a more classical field of theoretical computer science, which is complexity theory, the computational power is not that important here. And so most of the tasks which you want to solve are some sort of agreements tasks between different nodes under a condition that there are possible failures. So it doesn't really matter the computational power, but but there's uncertainty. Anyhow, so you have n processes which want to perform a certain task, and then you have to choose a model of communication. There are many choices you can make. So a classical choice of model of communication between nodes is that you have a network, could be a complete network or maybe partial network, and they communicate by means of message passing. So you can send, so a certain node I can send a message to node J with a certain content, and there will be a list of axioms or conditions which may be satisfied depending on what you want to assume. So I'm not going to go into this because I'll look in a different model, but in the model of message passing, a typical axiom would be that if node I sends 2 messages in node J, then if they arrive in the same order. But there is no guarantee, for example, that they arrive at all. But if they do, then they arrive in the same order. That would be typical condition. There are other conditions like this, livelihood conditions. So that's something people studied a lot. The other model of communication, which I want to talk about, for which there are good simplicial models, is so-called read-write communication. In this model, you have a common register, which as a processor communicates to, and each one can perform one of the 2 operations. It can either write or read from the register. And there are choices you make. So since this is a very applied area, you have a lot of choices you have to make, right? Because you make a model. So you can assume that they write only in their own register and read from other registers. So immediate snapshot, for example, is the assumption where they perform 2 operations. One operation is that they can write into the register whatever information they want to write there. And in the other operation is that they read the entire list of registers for all of them. So in one computational step. It's important to say that they don't read it one by one, because since we have a timing model at the same time, you don't want things to happen in between, right? So when you do this actual implementation, there is a notion of critical interval. And the critical interval means that you do something and you assume that the next sequence of operations happens so fast that nothing else will happen in between. This is a critical interval. Because if things happen in between, you read something, for example, typically you read something which is in some cell, and then you in some register, and then you make your conclusions about it. But in the meantime, some other guy has written something else there, and then you do something, things go wrong. Anyhow, so and then there are other models where you assume other primitives, but like I said, we will not look at all of them. This is just a plethora of various models. And like to the choice of possible failures, the 2 standard ones will be either a crash failure or a Byzantine failure. So a Byzantine failure we already discussed. This is sending corrupt information. A crash failure would be that the information may not arrive. So that's a simpler type of failure. So a typical example of a crash failure happens when a conference organizer asks for an abstract for the talk, right? Then you don't hear back. So you don't actually know, is he slow or did he crash, right? And then you have to make decisions under uncertainty. Whereas Byzantine failure is that he sends you a different abstract, right? So then, of course, it's easier to agree on things, for example, to solve things when there are crash failures than there are Byzantine failures. Typical protocols which will solve things when there are Byzantine failures present would be majority voting under assumption that a certain fraction is still healthy. Of course, if everything after a certain degree of corruption, as a whole network is, you cannot do anything. So, and then there are different choices of timing models. Asynchronous means that you do not have a synchronization between them. Synchronous you do. More interesting is asynchronous, but then you have all these models, and then there is an area which I will not talk so much about, but in this area people reduce one model to the other. So we're talking about impossibility results, which tasks are solvable in which models. They will simply prove a bunch of theorems, which will say that if it's solvable in snapshot model, then it's also solvable in this model and so on. So this is very helpful for a mathematician, because then you can work maybe hopefully with one model, which is a standard model, and whatever you prove about this will also be true for others, because there is a step of computational reduction of the other models to this one. So you're interested in impossibility results and also in computational results, like complexity, different types of complexity results. Okay, so I will only talk about this one standard model of communication, which I already started to define. The processes which I look at, so that will be shared memory, so they write and read from a common register, and each one writes whatever it wants. So since it can write whatever it wants, and we want to have estimates, we can simply assume that each time each processor writes its entire state there. So simply all information it has until this point, which in the beginning may be just whatever input value it has and its processor number. But as the communication goes on, it may write its state, whatever it has after a few rounds. And the snapshot we discussed this means in one atomic step means nothing happens in between, it reads the entire step. We allow crash failures, and these protocols are asynchronous and so-called wait-free, meaning that there is no upper bound on how long it takes to execute a step. So, and all executions are immediate snapshot, meaning that in each step, a group of processes becomes active, at which point all processes first write and then read together. So, and then also the executions are layered, meaning that it's divided into rounds, and in each round, each non-faulty process reads and writes exactly once. So actually, this can be reduced. So the bottom line is that all of this can be reduced to the model where you simply have a number of rounds, let's say 10 rounds, and in each round, there is simply a division into groups of all the processors, and then within each group, they all read and all write. So what happens in each round is simply defined, uniquely indexed by ordered partition of the set of processes. Okay, so it will be easier for us to work with this, because you can make simplicial models for different computational models, but they will not be as nice. The one you want to look at will be just a subdivision of a simplex, whereas these things will become more complicated topologically, and it will be hard to say. At the same time, from the point of view of computation, they are reduced to each other. So just to give you like a toy example, one such task would be assigning communication channels to the processes. So in this model, you have the following situation. So you can formulate it in different ways. You can formulate it, for example, as airplanes trying to land in the airport. But I'll formulate it in terms of communication channels. So in this task, you have a certain number of communication channels which you want to assign to whichever agents show up up front. And the number of communication channels is rather limited. So I don't know, maybe you only have like 5 communication channels which you can use. And the number of all possible agents which can show up could be in the millions. I mean, a whole database of clients. So if you want to assign a unique communication channel to a client, your solution is not going to be that each client simply has a dedicated communication channel, because there are many, many more clients than communication channels. The only hope you can have is that there is a limit on how many of them show up at the same time, and then you distribute them. So, like I said, another model you could imagine would be that you have planes landing in an airport, and you have a certain number of landing strips. And I think it's customary to assign a unique landing strip to each plane, which is trying to land. But there, potentially in the world, there are many more flight numbers than there are landing strips. So you can only hope to do it for a few at a time, and under these conditions of uncertainty, right? So they communicate like this. So each one, in each round, each one communicates whatever information it has. So in the beginning, it's just his flight number, but then maybe more, depending. And then he reads what the other wrote, and then he does the decision. So I don't know if 2 planes are arriving, and he just communicates his number. Then he reads, is there anybody there? For example, if he doesn't see anybody, he says, I'll take the strip 1. That's what could be one protocol. Right, and then if he sees, I see the other guy, I don't know, he can make a decision let's say two guys are arriving, and then there are two landing strips, and he just sees, if he sees the other guy, he compares his flight number to the other guy, and then he says, if mine is small, I take the left one, if it's bigger, I take the right one. All right, so the problem is, if it will not work like that, because if they arrive at the same time and they both read and they both write, then they both see each other and they will distribute correctly between the landing strips. But in this model, we also allow the possibility that the first guy arrives, and then he does this step, read, write, and then the second guy arrives and does read, write. So when the first guy arrives, let's say the first guy arrives and he has one of the two who has a bigger number, he arrives first. Then he looks, but he doesn't see the other guy, so he doesn't actually know what the other guy's number is. So then he will pick the first lane. Then the second guy arrives and he sees the first guy, and he sees that he has a bigger number, so he also picks the same lane. Because the second guy would need to know if the first guy saw him or not, but he cannot in this model, so he would have to go in another round, and so on. Now, in this model, we also assume the fresh memory, which means that after each round, the memory is erased, so each time the guy only sees what whoever wrote in this round. Of course, he has a memory himself, so he will see, let's say in the second round, he sees the other guy, he will also see what the first guy saw in the first round, because he will write his entire state into it. So potentially there is more information, but actually you can prove that it's, and the simplicial model is actually very easy to prove that if you have two guys arriving, they will never be able to solve it for two strips. So for two guys, you need three strips. And for the three strips, it will work with the protocol, which is here under the last point. They can communicate like this in this model, which we're talking about, that they simply read and write their number. And the first guy, so each guy, his protocol is like this. He looks in the memory and he doesn't see the other guy, he picks the first lane. But if he sees the other guy, he compares his ID with the other guy, and then he picks either the second or the third, depending on what he sees. So this one will work, and this is actually optimal number of lanes for two guys. And you can ask the same question for higher number, but I don't think this is known. So there are further examples of tasks, so just list them so that you get a flavor. So you see they're quite different from the tasks which appear in usual complexity theory. So the standard task actually, which was in the beginning of many of these things, is so-called binary consensus, where each process starts with the value 0 or 1 and eventually decides on 0 or 1 as an output value. And there are two conditions. So first of all, they need to come to a consensus, so they need to agree on the same value. And second, if all of them had the same value to start with, then they need to stick with that value. So without the second condition, you could write a very simple protocol, because each one would simply decide 0, then they have a consensus. Right? But there is additional condition that if they have 1 to start with, then they need to actually come up with 1. So that was actually at the beginning of this whole field of theoretical distributed computing, because they were designing various chips, and this result showed up, formulated in a little bit different language, where they could prove that in the computational model which they were implementing, binary consensus is not solved under the asynchronicity conditions which they had, which is of course quite bitter, because binary consensus is a very basic task. So basically, if you cannot solve binary consensus, then you need to implement more primitives. Then this developed, and people started to look at things like K-set agreement, and it turned out that also quite interesting. And the K-set agreement tasks, they all have an input value, and eventually you have to decide on the output value, with the condition that the total number of values which they have to decide in the end should be at most K. And at the same time, the only values they're allowed to pick are the ones which were present in the input values. So if you think about it, then one set agreement is actually binary consensus. So they have to decide on one, and they are not allowed to pick something which was not present to start with. And it turned out that even these things are not solvable. So if you have 100 processes and they all have very certain, and then they need to decide to agree on 99 consensus, so they have to somehow eliminate one value, still you can do it in the standard model. The last thing is the one which is I will get to in the end, which leads to interesting questions about labelings of vertices in simplicial complexes and triangulations of simplices. It's called weak symmetry breaking, and in this task, it's an inputless task, so processes have no inputs, just their IDs, and they need to pick outputs from 0 and 1, such that not all processes pick the same output, and they're only allowed to compare their IDs. So it should be protocol, which is ID compare based protocol. That's a standard requirement, because otherwise you could have protocols which refer to numerical values of the IDs of the processes, which is not something which makes sense. So they only can compare so that they can break the symmetry, but right. And then you need to distribute them into two groups, and each group should be non-empty. Okay, so let's now get out of this distributed stuff and try to think simplicially. So the simplicial complex is lurking in this whole framework. So the first and the simplest is a simplicial complex of initial configurations, so-called input complex. So I could have, let's think back to binary consensus. Let's say I have n processes. Each one has an input value 0 or 1. And I want to have a simplicial complex where vertices are all pairs of a processor and a possible input value. And the simplex is any consistent input value assignment. If you have no conditions, then any value assignment will be consistent. So if you have n processes, each one can have 0, 1, then you will have 2 n vertices. And this, because you will have a vertex name of the process and 0, or name of the process and 1. And any collection will be consistent, except for one condition, that each processor can only have one input value. So you will have 2 n vertices, which are in pairs, and any simplex is allowed, unless it contains one of the pairs. So if you think about this, this is just a triangulation of a sphere. You can, okay. The second simplicial complex, which is present here, is the output complex, which is constructed exactly the same way. So the vertices are all names. Their names are name of the number of the processor and their output, its output value. And you have a simplex if this configuration of output values is allowed. So in the binary consensus, you will only have 2 simplexes, one all 0 and one simplex all ones. That's a simplicial complex as well. Then the interesting part, which depends on the model you assume, will be a simplicial complex of all possible execution. So that's so-called protocol complex, and this is actually the center point of this whole development. It's so-called protocol complexes. So in protocol complex, you construct like this. So each process has an algorithm which it will perform, which in here is called protocol. It's just a name for it, for algorithm. So they have different protocols. In many models, they actually have the same protocol. And then what you want is you want to have a simplicial model for all possible executions, which can happen if they perform their protocols. Since the timing is asynchronous, there are many different possibilities, who comes first and so on. So there are total number of executions. If you say limit number of rounds, then there will be a certain number of executions which they can do. And you want to have a simplicial model for that. So in this model, the top dimensional simplices will be all possible executions, and the vertices will be all views of processes on what executions, what did the execution look like. Okay, so there are many different ways what the process is solved as the computation unfolded, and any set of consistent views will be a simplex. And in this model, actually, one can also show that any set of consistent views can result in at most one execution. So either there is no execution which has this views, but if they're consistent, then there is at most one. You can uniquely backtrack the whole execution from what they saw, all of them together. So I don't know. So this is very similar to also there are different models where people connected to logic, where you can have let's say you have the top dimensional simplices are models of the world, or possible philosophical models of the world, but each one sees it in a different way. So you have local views of what things look like, and then you have a simplex on a set of consistent views. So if there is I mean, they can be inconsistent, so there is no model where they see these things at the same time. But if there is, then you put a simplex. This kind of thing here as well. And then then what you want to do is, of course, you want to have this is just to produce models for input, output, and also for the execution. But then you want to do two things. So if you need two more things. One thing you need to do is you need to specify a task. So you need to actually have a simplicial language to tell you what task you're looking at. So the things I was looking at before, for example, binary consensus or weak symmetry breaking, you need some sort of simplicial language to say what a task is, what is it that you want to achieve. And the other thing is you want to say simplicity is that the protocol you designed will solve this task. So you need two things like that. So the first is accomplished by so-called task specification map. And in this map, you simply, for each input, you simply want to say what are legal outputs to this input. For each input, you want to say what are the legal outputs to this input. This is something, of course, this is actually the standard way without simplicial content. This is the standard way the task will be specified in distributed computing. So it's simply for each input, as they will tell you what are the legal outputs. It could be more than one. In the simplicial setting, it will not be simplicial map, but it will be what's called a carrier map. So each simplex will map to a simplicial subcomplex. That's a task specification map. Then you will have another carrier map called execution map, which will go from the input complex to the protocol complex, which will take each input and map it to the subcomplex of all possible executions under this input. That's what's called execution map. Then there will be a decision map, which is simplicial, which for each execution tell you what the output is. So when the execution ran, you will need to know, now the answer is this. So for each execution, you say this is the output. And finally, there will be a commuting diagram. I think in one of the previous talks, there was mentioning that every topological, there was commuting diagrams. There is sort of commuting diagram here, not for simplicial maps, but for carrier maps, but still. And it's a condition which will bind it together and will say that this protocol solves this task, which will involve the task specification, decision, and execution maps.
Did you,
Yes.
did you say the carrier maps need not be simplicial?
Well, they might be, but in general, the carrier map will simply map a simplex to a subcomplex.
Simplex to a subcomplex.
Right. There are more conditions in this, but in general, it's, yeah. But they all go the same dimension and so on. It's the same dimension. They'll go with pure. Yeah. In general, carrier map, it could map just a single simplex, but in general, yes. Yeah, because I mean, we're not making it up, right? Because we have to, we're trying to do, these things exist, and these things got studied by these people. They don't actually need us. So, and then you can make a different model, but it will not be what they care about, right? So, but you really want to model for each input. Unfortunately, there could be more than one output, which is legal, right? So, going back to I don't know, binary consensus. If you have a simplex in the input complex, which has both zeros and ones in it, then either one of the output simplices will be allowed. But if they're all zeros, then only one is the one. So you will have to map one simplex to two, because they're both. Right, so actually that's exactly the next slide. It's very convenient. So it's simplicial for the binary consensus. You, as an input complex, you will have this complex that you were talking about, which is a subdivision, standard subdivision of the first one, simplicial subdivision of a sphere. If you want to make one, the first one you make is, well, not the simplex itself, but the one with the Z2 action. That will be the one, and the output complex consists of two disjoint simplices, and this is a task specification map, which is exactly what we just talked about. So if they're all zeros, then it's a single simplex with zeros. If they're all one, then it's a single simplex with ones. But if they're both present, then it is a union of the two. So to the protocol complexes, and this is important here, the model for the protocol complexes for this round model is the following. So let me just switch now to the combinatorial language and tell you what the simplicial complex is, and then with some work one can connect it back to the distributed setting and see how this is correct. So the complex, and in fact this complex appeared in many different contexts in various situations before, also in the work of Tom. Somebody sent me a reference to some old paper of Tom, where this kind of subdivisions appeared in also topology, but here they appear naturally as protocol complexes for this one round protocols. And this is what we call standard chromatic subdivision. And in this subdivision, you take a simplex, and rather than doing the barycentric subdivision, which would put only one vertex on each simplex, you put several ones. What you do is you take a barycenter of each simplex in your as a boundary simplex, it's a smaller dimensional simplex, barycenter, and then you shift it towards the end vertices in all possible ways. So on the edge, for example, here, is there a pointer on this one? Did we know? I don't know. In the middle. Look at this. Okay, so then it's green. Okay. So for example, here there should be barycenter in the middle of the edge, but rather you move it one way here and one way there, and then you have this two vertices. And here too, you should have a barycenter, but then you move it one way in each direction. You move it opposite to the, always opposite. So actually it's a bit confusing, but here this one is coming from this vertex. Anyway, and then there is a way you can describe how you connect them. So the simplest way to describe it is to simply give a combinatorial description of all the vertices and all the simplices. Okay. So the definition, I can tell you what it is the following. The vertices, so you have n elements, in this case 0, 1, and 2. Okay, so n is equal to 3 here. In fact, in this case, estimated here n is equal to 2. Anyhow, so you have 3 vertices, and then the vertices are all possible subset of the set of the vertices with one of the elements chosen. Okay, so in the barycentric subdivision, vertices are just subsets, right? And here it's subset with one of the elements chosen. Okay, and the top dimensional simplices, like I said, will be all ordered partitions of the set of the vertices. So, for example, the middle triangle will correspond to just ordered partition consisting of one single block, where 0, 1, and 2 are all together, bundled up together. And then this one will correspond to a ordered partition where you have 2 blocks. The first block is 0, and the second one is 1, 2. This is just combinatorial. This is just combinatorial labels. They correspond to executions, but if you don't care about executions, you don't have to care. This are just this is how it is. So each top dimensional simplex just the ordered partition of the labels. Okay. If you want to tell what are the vertices of it, all you do is you simply pick the vertex you want, one of the elements, and then you take the union of all the blocks which are to the left of this block. So if your ordered partition is 0, 1, 2, and then you can either pick 0, and it will only see 0 itself. It will be 0, 0. It will be this one. Or you can pick 1, but then it will see all 3, 0, 1, 2. So that will be one of these two. And the other one will be 2. And the set is 0, 1, 2. Okay. So that's we call standard chromatic subdivision because unlike the Bayesian subdivision, if you color the vertices, you can easily extend the same number of colors. And yeah, on the left, of course, that's what happens. You only have 2 guys. Okay. And the way it's formulated, you can immediately see that it's inheriting on the boundary. It inherits each other. So what happens on the boundary is exactly just the same as for the Bayesian subdivision. It's a lower dimensional one. So because of this, you can iterate it. So in other words, what I see here, I would call it the first standard chromatic subdivision of the triangle, and I can repeat it again and get the second chromatic subdivision and so on. The same I can do for this. So I will have 3 edges. In the second one, I will have 9 edges because I will do the same to each one of the 3, and so on. So I'll have just an edge which is subdivided like 3 to the n smaller edges. For triangle, I'll have a higher number. Okay. Any questions about this things?
I'm not quite seeing why this is the weight-free layered median snapshot.
Okay. Yeah, so that you see is enough. But well, okay. So but that's not actually. So this is a mathematical model. If we don't care about the supercomputing, we don't care about it, right? And so yeah, but how to connect it back? All right. So like I said, so each execution. So let's say the middle. Let's take the middle triangle. So that corresponds in my labeling to just a single block, 0, 1, 2. In the execution model, it corresponds to the one possible execution in which all of them arrive simultaneously. This triangle here will have ordered partition label 0, and then another block 1, 2. It corresponds to the execution where first the guy whose name is 0 arrives, and after that the guys whose names is 1 and 2 arrive simultaneously. All right. And there are, for 3 guys, there are 13 possibilities. In general, it's called the Bell number, weighted Bell number, whatever. It's exponentially growing, doubles now. It's a very large number of all possible executions, even in the first step. In fact, for the weak symmetry breaking, the most interesting case, the first interesting case, is for 6 processes, because it's the first non-prime power. And so even in the first execution, the number of syntheses will be enormous, and one is interested in this third one, so one talks about millions of them actually very quickly. So these are small models. Okay, so that's how it connects, okay? And so this is one round execution. So these are triangles, are possible executions. Vertices are possible views. So if I have a vertex here whose label is 2, and then subset of the total set 0, 2, and I read process number 2, so 0 and 2 during the execution. Each processor saw himself, but he also may or may not have seen someone else. This is how it connects back. Okay. If you repeat the rounds in the execution, then you just do an iterated subdivision. Yeah. Okay. You can repeat this subdivision, iterated, sorry. Okay, I think, so I have 2 more things, but, okay, so I think I'll skip one of the 2 things. So I have I have a description of the whole model, and I also have the weak symmetry breaking, but I really want to go to the weak symmetry breaking because this is where we still have open problems which we can formulate mathematically. And so let me go to this, all right? Because I want to get to some mathematical question at some point. So I think the best way is that I will just do it on the slide. Okay. So let me formulate. Let me formulate the question directly, and then we can connect. So okay. So I want to formulate now a mathematical question, okay, which does not involve distributed computing, and then we can connect it back and see what's wrong. The mathematical question is as follows. I take a simplex, an n simplex. Okay, in this case, a triangle. Okay, and I can do the class I'm looking at are simplices, which I have chromatically subdivided a number of times. So a t-iterated chromatic subdivision of an n simplex. Okay, this is the stuff I'm looking at. So let's say triangle, which I subdivided a few times, for example. Okay. And I want to know, do I have a certain 0, 1 labeling on the vertices? Yes or no? Okay. The condition on the 0, 1 labeling is the following. The first condition is that I will have no top-dimensional simplex, in this case a triangle, where all of the labels are the same. I will have no monochromatic top-dimensional simplices. Okay. And the second condition is, okay, let me first say what it is for a triangle. The second condition for a triangle will say this of the following. The labels of the vertices in the corners are the same. The 3 vertices have the same label. And the labels on the edges are connected in the following way. So I label the corner vertices. Let's call this one, let's order them. Let's say this is the first one, this is the second one, this is the third one. And then orient edges always from the smaller one to the larger one. So it goes from this to this, from this to this, and from this to this. And then my condition is that the labels on the edges will be the same if I read them in this direction. Okay. So in general, if you have an n simplex, if I take any 2 simplices, any 2 boundary simplices of the simplex with the same number of vertices, okay, and I ordered the simplices, I ordered the vertices of the whole simplex, there is a unique identification between 2 boundary simplices of the same dimension, which respects the linear order of the vertices. Okay. And my condition is that my labeling should respect that. So on each smaller dimensional simplex, the label thread should be the same if I identify with this way. So there are 2 ways to formulate this condition. Either as I did with a simplex and this condition on the boundary, or I could start by gluing together. I could start not with a triangle, but I could glue together. I would say I have a triangle, I identify all 3 corners into one vertex, and then I identify the edges in this arrow direction. So it would be arrow going from here to here, an arrow going from here to here, and an arrow going from here to here. I'm sure you saw it in some textbooks in topology. And you glue it together, and then you have a new topological space, which will be more complicated than just a simplex. And that you can do with any simplex. So I could take any simplex and identify. So I will have a semi-simplicial set where I will have only one simplex in each dimension because I identify them, okay, which is then t-fold subdivided by 0, 1. And the question is, do I or do I not have such a 0, 1 labeling quantity? Okay. So that question is equivalent to asking, can I or can I not solve weak symmetry breaking in T rounds? Okay. Because of this formulation, actually, or mathematically, you can easily see that if you have such a labeling for some t, so let's fix n. If for some subdivision, let's say a triangle, if there is a some subdivision of a triangle for which I can find such a labeling, I will also be able to extend it to all higher ones. Something you can kind of easily show with this combinatorial model, or trivially show from computer science, because it's obvious to any computer scientist that if you can solve it in T rounds, then you can solve it in higher number of rounds. But for with the smaller, you have to, say what the labels are, the new ones are, but it's not. Okay. So the answer to this question is no. The answer is okay. The answer to the, so this leads to the question, for which n can you find it at all for some t, right? So that would be a question, can you solve the weak symmetry breaking for n processes? And that one is actually known. So the answer is you can solve weak symmetry breaking if and only if the number of processes is not a prime power. Okay. So that's a theorem in theoretical. So that's a theorem by Herrlich and Schmidt, which have proved some time ago, maybe 20 years ago, that you can solve it if and only if it's not a prime power. The next question is, how many rounds do you need? Okay. So let me maybe go through. I'm sorry, I will have to go through some slides which I didn't want to have to talk now because I want to get to some. Okay. So this is simplicial formalization, which we didn't go through. Anyhow, so just because before I go through, so this is a book on this topic. It's called Distributed Computing through Combinatorial Topology, which appeared in 2014, which is by two co-authors of mine and myself. The two other persons are in computer science. Right, and anyway, so let me just get to something which I can talk about. Right, so maybe from this point of view, this is just repeating what I said already, just with terminology. Sorry, with notation. Okay, so so a labeling on the you see, this is simplex. This is the T's standard chromatic subdivision with, and the labeling on the vertices is called compliant if it satisfies this condition I was talking about. So if you identify boundaries simply of the same dimension, it's the same. So, like I said, you might as well label the things in this convoluted topological space if you want to. And so, and the main goal is to find this compliant labels. Okay. So this is just formalizing what I said already in words. Okay. There is a theorem of Herrlich and Schmidt, which said that you can do it if and only if, well, actually, okay. So actually, the whole theorem, what I said is actually Herrlich and Schmidt, Weisbaum, and I forget this theorem. So they proved it's impossible if it is a prime power. And Castaneda and Weisbaum proved that it's actually possible if it's not a prime power. So then you can ask a question, then you can concentrate on prime power, not prime power. So the first one is 6. And you can ask yourself, what is the value of T, which you need? Because that would be a question of round complexity for the protocols. Okay. So, oops, sorry. So the known upper bounds, due to Atiyah, Castaneda, and Paz, was that the T is at the order of magnitude of n to q plus 5, where q is the largest prime power dividing n, so potentially it could be close to n itself. In particular, for 6, there need at least 17 rounds, and there's actually it's just a theoretical proof. There's no protocol, which is still the case even from my theory. Anyhow. And so maybe I finish with this. So 5 or 6 years ago, we were able to prove something quite interesting, namely that if you do have, if there exists such an identity of binomial coefficients, so a certain sum of binomial coefficients is equal to a certain other sum of binomial coefficients with almost no conditions. If you have that, then you can actually solve the weak symmetry breaking in 3 rounds. Okay. So the conditions are written here. So you just have the sum, and then this A is here. These are binomial coefficients. So this A's are between 2 and n, well, between 3 and n minus 1. And B1 is between 2 and n minus 1, if that exists. So that would be an example of such an identity. Or is this here? I'm saying this as the first 2. If you have it, then actually you can solve it very, very rapidly with a weak symmetry breaking, namely only in 3 rounds, which is quite an unexpected result because there is an infinite number of values of n for which you have such an identity. We cannot characterize the set, we don't know what they are, but we know, for example, that all the multiples of 6 belong to the set. So for each multiple of 6, we can produce such an identity. And so it means that there is an infinite number of values of how many processes there are in which you can solve it in a constant time, in a constant number of rounds. And it is unknown what is in general the case. Can you always solve it in a constant? So actually there is some schism there. So I think yes, but Morris thinks no, Morris thinks no. Okay. Anyhow, so that's the rest would be just details of this proof, but I think I should stop here. And that's it.
Are there any questions?
So you mentioned the community in distributed computing. Do they use these kind of protocols coming from simplicial complexes to get out of it?
That's an interesting question. Is you don't use it because there are no protocols which come out of it. This is a short answer. So first of all, these theorems which I told you about, they prove them using similar language. So it's not like they didn't know or care about simplicial complexes and then they saw the light. That's not like this. They actually do. So all of these proofs are like this. They look at the simplicial complexes. They look at things which they thought were subdivisions. They couldn't prove it, but they thought they were subdivisions and so on. So first of all, this whole context has been present even prior to our work in the distributed computing. Okay. Then it's a question of what is a protocol. Okay. So protocol is just so that people get confused, including myself, for a long time. The protocol is just an algorithm. It's just their word they use for an algorithm in distributed setting. Okay. And we are used to algorithms formulated in a verbal way. So like in my example of landing strips, I had a protocol and my protocol said, I do that, then I do that, then if I see this, I compare, and then my choice is this. Okay. This is what you think should be a protocol. But that's not how these things are proved, because once you formulate them mathematically, like this, with labelings of this, for example, we can show, as a special case of this theorem, that for 5 simplex, if you give me a 5 simplex, you have 6 vertices, and you take the third chromatic subdivision of this, which will have an enormous amount in thousands of vertices and in the millions of simplices, then I will be able to find a labeling. Okay. So fortunately, it's not like a probabilistic proof or something like that. So we can actually construct a labeling. I can actually construct with some complicated procedure, which starts with some labeling and then starts to fix it by using various results from matching theory and so on. And eventually it kind of gets to some labeling. But then the question is, then what? Okay. Because then you have this labeling, and basically after this, I can write a protocol. And my protocol will be very, very, very long. And each line of this protocol will be the following. If I'm processor I, and I have seen this, this, and this is my view, then I decide 0. The next line will say, if I'm processor this, and I see this, and I decide 1. I can translate it to a protocol, but it will be extremely long protocol. So Formulate is solved, but it's not, I believe their word for this is natural protocol, which you would usually associate with an algorithm, which would be like a verbal description, which would not be of the length of, I don't know, 16,000 lines or something like that. For a single, just for 6, not for n. For n, it would depend on n, the length of the protocol. So you have formally a protocol, but for some people, they'll say, no, they need a natural protocol. But there is no real formalization of what a natural protocol is. You can have different conditions and so on. And so, yeah, so the answer is no. Producing explicit protocols from these results is actually a matter of research. And it's kind of mysterious. And also it's very strange because from the point of view of symmetry breaking, it shouldn't matter if you have 6 or 7 processes, but it does.
Other questions?
Can we use these techniques to get some lower bounds on communication complexity?
Well, what do you mean by communication complexity?
How much you're solving not sense of trying to work matrices or something, right? How much they can.
So I think so in these models usually there is no you do not take into account how much data you send in one step. So you can use it to get bounds on how many times you send things, but it doesn't take into account what you have to do locally, and it also doesn't take into account how much you send. But it will, like I said, like how many rounds will you need to solve something? Yes.
So this might be off topic, but is there a connection between this distributed computing and random computing?
Okay. I haven't looked for one, I'm sure.
Any other questions? Well, if not, let's thank Dimitri again. And I believe next we have 2 parallel sessions. Coffee break. And what time do the parallel sessions start?
4.
4.
Okay.
Very good.